So now we're going to work towards our wave equation from this discrete situation that we looked at a second ago. So here's the equation we have for the acceleration of yr as a function of the positions of the adjacent masses. What we're going to do now is let b go to delta x, so being some small infinitesimal slice of position, and the mass will go to rho delta x, so the linear mass times delta x. In this way, the amount of mass on the string stays the same, but the masses get closer together as we let delta x go towards 0. We also write yr as a function of x and t, so we have y of x and t. So b goes to delta x, m goes to rho times delta x. So rewriting this equation up here with the new notation, we have the second partial time derivative of y is equal to t divided by rho, and we've got a delta x squared on the bottom here. One factor of delta x comes from the mass, the other factor of delta x comes from the b. And then we have our y's here, one at yx minus delta x, y of x, and x plus delta x. So that's used to be our yr minus 1, yr, and yr plus 1. Now we're going to expand each of these to second order in Taylor expansion. And we need second order, otherwise there are too many cancellations and we end up with a 0. So to second order the Taylor series, we have y of x and t. Then we have a plus or minus delta x times the first spatial derivative. So depending on whether you got plus or minus delta x here, you get a plus or minus here. Then we have a half times the square of plus or minus delta x and the second partial spatial derivative of y. Now this sign here goes away because of the squared here. Substituting that back in, what we find is that the first order derivatives cancel because we have a minus delta x and a plus delta x here, so when you add those together they cancel. But the delta x squared means that the second spatial derivative does not cancel. And so when you substitute those Taylor expansions into this and cancel everything out, what we get is this equation here where we have a delta x squared on the bottom from this factor out the front, which will cancel this delta x squared, and now we have a second order spatial derivative of y. And what that gives us is this equation here, which is the wave equation that we've been trying to derive. So we've got a second order time derivative on this side, second order spatial derivative on this side, both partial derivatives, and this part here, this t divided by rho, that's the thing which gives us the velocity of our wave. Let's have a look at this wave equation now and see if we can figure out how fast a wave is going. So we're going to try a function of the form y kx minus omega t. This function we hope will solve our wave equation, and we can check that pretty easily. We just substitute into these derivatives and see if we can find a condition that works. So the second time derivative of this function y gives us an omega squared out the front from this omega t, and the second derivative of y. Second spatial derivative is almost the same, except we get a k squared instead of an omega squared, and the y double dashed. Now, from these two equations, we can see that the second time derivative of y is equal to the second spatial derivative of y with this factor omega squared on k squared in front. And this equation here is exactly the same as this equation up here, provided omega squared on k squared is equal to tension divided by the linear density. So, provided we can satisfy this, then this function here solves our wave equation. So that's great, we have a solution to our wave equation. Let's have a think now about this function y, kx minus omega t. In order to see how fast a wave is going, what we need to do is set kx minus omega t to be some constant. Now, if the argument of this function y is a constant, then the height of the wave is constant, and we're sort of following along a peak of the wave, if you like. So you can see that as t increases, negative omega t will be going down, and in order to counteract that, then kx must be increasing. So as time increases, x increases. So in this way we have a wave evolving in the positive direction, like this. So imagine we're following a point here in the wave, this red point, and t is increasing and x is increasing, and we're following along the peak of the wave where b is some constant. So to find out how fast the wave is going, we just rearrange this equation here, and we get x is 1 on k times b plus omega t, And the speed, c, is dx dt, which is omega on k. So c, the speed of the wave, is called the phase velocity. And for the string, c is equal to the square root of the tension divided by the linear density. Now in the particular case where the function y is a sine or cosine wave, as I illustrated up here, we can identify k as 2 pi divided by the wavelength, so that's the distance between the waves in the x direction, and omega is 2 pi divided by the period, so the period of the wave is the time between passing wavefronts. In general, the wave equation can be written like this, where instead of the t divided by rho, which is specific to the wave on the string, in general this factor out the front here is 1 divided by the square of the phase velocity.